Morning, everybody.
Good morning, sir.
Good morning, sir.
Any question from previous classes? Anybody has any question? This is the last slide we showed and discussed in previous classes, a previous class. So we discussed the relationship between line direction, slip direction, Burgers vector of both screw and edge dislocation. But one important statement is this: irrespective of type of dislocations you are considering, the nature of the deformation will be identical. Each offset created will be equivalent to one Burgers vector of the dislocation. So this is the last slide. Again, we showed you exactly what was happening. Now we talked about at the beginning, the theoretical shear strength is at least 500 times more than the strongest material known to us. And this is because we have to rupture the bond. You have to rupture the bond between the atoms if you glide one slip plane over the another plane. So this rupturing of bond requires a huge amount of stress to create this. Then we introduce the concept of dislocations. Okay, we know edge and screw dislocation. But what good does it do to understand this behavior? It is so low, the strongest known material's shear strength compared to the theoretical shear strength of the material. Now you please carefully look at this figure. This is an edge dislocation. Extra half plane is the red color. For the sake of clarity, I put the color. I applied shear stress. What happens? You see the lattice is bent around this extra half plane. So when I apply shear stress, what happens? Look at this ABC. This dislocation So this extra half plane red gets tied up with this continuous plane, green color plane, and this is the slip line, a slip plane, this horizontal line, and snaps the bottom portion of this green color plane away from the green color plane. So what happens? The red took the bottom of the green color plane away from the continuous green color plane, and now it becomes a continuous plane. Now the green color plane, which was a continuous plane, now becomes an extra half plane. So the edge dislocation previously was here. This is the symbol of edge dislocation. This is the symbol of edge dislocation. So edge dislocation was lying here. Now it moved to this place on the slip plane. Now this green color plane, due to the application of shear stress, snaps away the bottom portion of this pink color plane and becomes a continuous plane itself. And this pink color continuous plane becomes an extra half plane until, and this goes on. So you break the bond between atoms one at a time. In previous slides, you are breaking all the bonds together, snapping all the bonds. So that's the reason theoretical shear strength of a material is so high. You have to break the bonds between atoms all the atoms at the same time along the slip plane. But in this model, you break the bond here, one bond at a time, one bond at a time, until the last plane becomes an extra half plane, and dislocation escapes the sample and reaches the surface, and it creates an offset. This is the magnitude of this offset, and the offset is the magnitude of it is the Vargas vector's magnitude. This offset is the magnitude of the Vargas vector. Any question? So this is how you break one bond at a time, one bond at a time, instead of all the bonds simultaneously when you calculate the theoretical shear strength. This is how edge dislocation moves. The same thing, another picture, if you look at it, ball and stick model appears to be 3D. It moves, it snaps away this bottom portion, and eventually it reaches the hub. So one plane at a time, you snap the plane, breaks one bond, and creates an offset, which is equivalent to the magnitude of this offset is same as the Vargas vector of this dislocation. Any question? So that if the dislocation does not move, deformation means plastic deformation will not occur. So for plastic deformation, you need to move the dislocation, and dislocation motion takes place above the yield point. Below yield point, you are not able to move the dislocation, so deformation is only elastic in nature. It obeys the Hooke's law. Now if I stress it above the yield point, dislocation start moving, you create a permanent deformation which is called plastic deformation. If you remove the load, the elastic component of the deformation is restored, but the plastic component of the deformation is not restored. It becomes permanent, and that is the strain in the material. So there is a good example. Since you did not come to the hostel, you have no idea. So in common rooms, sometimes they have a big carpet laid down, which is not a permanently fixed. It's like satranj. Satranj, they can move it. If you want to drag the carpet, you cannot do it yourself, such a big one. But if you create a wave, a fold in one end and move that wave, you can reach the other end and create an offset. If you look at the caterpillar, how do they move? Please switch off your microphone. One of you have switched on your mic. Please switch off the microphone. The caterpillar, how it moves. If you watch a caterpillar carefully, you see towards the tail end, it creates a hump. And that hump tries to move towards the forward side. So a hump is created and the hump moves towards the forward direction to his head. And when hump reaches the end, it moves by a distance half the wavelength of this hump. Again, a hump is created at the tail end. This is how a caterpillar moves. And this movement can be correlated with the movement of an edge dislocation. Extra half plane snaps the bottom portion. So new extra half plane is created. It snaps the bottom portion. It becomes a perfect plane. And this becomes a extra half plane until it reaches the end. This is how a dislocation moves. And without the dislocation motion, you will not have permanent deformation. And slip takes place on the highest atomic density plane and the closed pack direction, always. So this is the 0001 plane of hexagonal closed pack, and this is the plane with a 111 plane of face-centered cubic. Same orientation. Look at it. A slip system, yesterday I mentioned that, is the number of distinguishable slip planes multiplied by the slip directions. FCC had 4 distinguishable type of 111 plane. 111, 11 bar 1, 1 bar 11 and bar 111. You may ask why there is no bar 1, bar 1, bar 1. That is the mirror image of 111. So there are 4 distinguishable type of slip planes are there in face-centered cubic. Aluminium is face-centered cubic. And what is the direction? Slip direction. If this is the triangular plane in the body of inside the FCC unit cell, each edge will be 101 type direction, each edge. So I have these directions, 101 type, the 3 distinguishable type of directions. The others will be mirror image. So number of planes 4 multiplied by number of slip directions 3. That makes 12 slip system. Now if I look at the hexagonal closed pack, this is the basal plane. How many slip planes are there? 0001 type 1. And how many slip directions 11 but 20 type? 3. So number of slip system in hexagonal closed pack is 3. Because of large number of slip system, face-centered cubic is ductile, tough. Hexagonal closed pack is not ductile or tough. And VCC I mentioned, it doesn't have a closed pack plane like 111 plane of face-centered cubic or 0001 plane of hexagonal closed pack. This is how the dislocation looks like in transmission electron microscope. Yes. Now, any question?
Sir,
Yes.
hello. Sir,
Yes.
the dislocation movement is related to the plastic deformation.
Right.
Then the elastic deformation is just the movement of the atoms in its lattice positions
You are
itself.
stretching the bond.
Hello?
You are stretching the bond. The atoms move from its equilibrium position slightly. When you release the load, it comes back to the original position. You see, other than at absolute zero, the atoms vibrate about its equilibrium position. And frequency of vibration is the function of temperature. Higher is the temperature, higher will be the frequency of vibration. And if the temperature is very high, they vibrate so much, you break the bonds and it melts. So you stretch the atoms by a fraction of a lattice constant in case of elastic deformation. But plastic, you see, the dislocation moves by 1 atomic distance towards the slip direction. And it restores the lattice after slip. Because everything moves like a march past. You see, the military are doing march past. If everybody moves 1 step forward, the formation looks same. So if the extra half plane moves by 1 atom distance, the slip region looks identical with respect to the yet to be slip region. So lattice is completely restored. Only dislocation line area that is distorted. That's the reason it is called localized lattice disturbance, a region of localized lattice disturbance. Okay. Am I clear to you?
Yes, sir.
Any other question?
So can you go back 3 slides?
Oh, sorry.
So before the slip system one.
What is the question?
So the previous slide. So before the start of slip
Said I went back 4 slides, but tell me which slide?
Sir, this means the movement, the caterpillar-like movement. That one.
You see, the caterpillar,
Yes,
this
sir.
is a corollary. Caterpillar creates a hump like this, and this hump moves from left to right, from tail end to the front end. When the hump reaches the front end, it moves by half the wavelength of that hump. So similarly, a corollary, extra half plane snaps the bottom portion of the next continuous plane. Extra half plane now becomes a continuous plane, and this continuous plane becomes an extra half plane. So this thing happens. One bond is snapped at a time until the extra half plane reaches the end of the surface.
Yes,
So
sir.
this
So my question is that you said the theoretical shear stress is more because as the slip plane slides, means the extra plane slides, so all the bonds are broken. So this way
yes.
also means one by one all the
If
along the all the plane.
forget about the extra half plane here, if the top portion if the top portion of this crystal glides over the bottom portion, this bond, this bond, this bond, this bond, this bond, this bond have to be ruptured at the same time. But due to the movement of the extra half plane, what do you rupture? This bond only. It takes the bottom portion away. The other bonds remain unchanged. There you don't break it. So one bond at a time. So that's the reason theoretical shear strength is much, much higher. If you have a defect like edge dislocation, you snap one bond at a time.
Oh, okay, sir. So because all the molecular planes along the slip plane, all the bonds for that are not
That is
broken.
the
That's
molecular
right.
atomic plane.
Yes, sir.
This extra half plane snaps only bottom portion of the next continuous plane. That's all. One plane at a time. But for theoretical shear strength, you have to rupture. If there is no dislocation, right hand side, to glide the top portion of the crystal with respect to the bottom portion, you have to rupture every single bond at the same time.
Yes, sir. Now I got it.
Okay, very good. Any question?
No more questions, sir.
Anyone else? Details chapter 4, 5, and 6. Anybody has a details copy, hard copy?
Yes, sir.
How many of you bought?
Yes, sir.
Yes, sir.
Sir, I.
So now, another concept we will introduce to you. Just 1 second. Now look at it. A perfect surface, polished surface. If slip takes place, you create an offset. You see a plan view like this for a single crystal. And the movement, the slip, took place by an integral number of the Vargas vector or atom spacing. So if you polish it, it goes away. Now, we'll introduce you to a new concept. How much stress is required to move a dislocation from the interior of a crystal to its surface? After a gentleman named Pearls, this stress tau p this tau p is the pulse trace required to move one single crystal from the interior of a grain to its surface. 2g 1 minus nu, you know g is the shear modulus, nu is the Poisson ratio, e to the power minus 2 pi w by b. What is w? W is the width of the dislocation. Sorry. W is the width of the dislocation, means the region, width of the region of localized lattice disturbance. And B is the Burgers vector. And we can write these things as the width of the dislocation. From here I can modify this derivation, I did not go through it. Since A and B are more or less same, minus 2 pi A by 1 minus nu into B. Okay, so displacement A, distance between slip planes, means parallel slip planes. The distance between parallel slip planes is small a, and B is the distance between atoms in the slip direction, which is the Burgers vector, distance between atoms in the slip direction. And W is the width of the dislocation. Now, higher is the pulse trace, more difficult will be to move a dislocation from its center to its surface. So tell me, if the width of the dislocation is large, what will happen to tau pi? Large or small?
Small.
Huh? Minus 2 pi w by b.
It would be reduced.
Huh?
It will get minimized, it will get
It will
less
be
and less.
reduced.
Tau p will be very big. Is in the denominator, 1 by e to the power 2 pi w by b, because there's a minus sign here. So the Burgers vector, if it is small, the pulse trace will be less. So that's the reason slip takes place in the closed pack direction. Distance of atoms in the slip direction should be as small as possible. Now what happens to the W? If the width is very large, tau p will be less. So generally, metals have a wider dislocation weight compared to ceramics. So metals are easier to deform than the ceramic. You follow what I'm saying?
Yes, sir.
Yes, sir.
And then what is the relationship between A and tau p? Larger is the A value, smaller will be tau p. So why slip takes place in the closed packed planes, highest atomic density planes? Because they are widely separated planes. And if they are widely separated planes, their A value will be large and tau p will be small. So for easy glide of dislocation, you need tau p should be small, pulse trace should be small. For that you need wide dislocations, small value of Burgers vector, and widely spaced plane so that the A spacing will be large. Now another term we will introduce to you. This is a single crystal, a cylindrical shape, a single grain. The cross-sectional area A, applied load is P, and there is a slip plane at an angle. And you know, when you applied in mechanics, any stress you applied, it has a two component, a normal component and a shear component. And normal never ever cause deformation. Shear does. Shear component does. So when I apply load to this cylindrical sample, on the slip plane there will be a shear component and a normal component. The shear stress resolved on the slip plane in the slip direction, let us call, will be total load P cos phi, a cos lambda divided by A by cos phi. A is the cross sectional area. So I take the projected area, this will be A by cos phi. So I can write it P by A cos phi cos lambda. And where tau r is the resolved shear stress. So there is a minimum value required to initiate slip on a slip plane. So if I apply a shear stress, any value, it doesn't mean it will deform. The yield strength you studied in your mechanics class, that's for a polycrystalline sample. Many grains were present. If I consider one grain, one single crystal sample, the resolved shear stress on the slip plane along the slip direction tau r is P by A cos phi cos lambda, where tau r is the resolved shear stress. So when the resolved shear stress on the slip plane in the slip direction, this is my slip plane and this is my slip direction, reaches a critical value, then and only then dislocation motion will start. And this minimum value is called critical resolved shear stress. Critical resolved shear stress. And tau r is maximum when these two angles are equal to 45 degrees. Any question? These are the problems from Callister book. You can solve it. I'll not do that. Read the solve the end of the chapter problems from Callister and Shackelford. Okay, this is important. I'll skip this slide. So slip system I mentioned, slip plane multiplied by slip direction for FCC. What I mentioned, it is shown here. Total 12 slip system. HCP has 3, BCC 48, but none of them are effective. Cross slip I already mentioned. Climb I mentioned. You see there is a vacancy there. Vacant side, atoms move from here to there. So extra half plane climbs from here, this position to that position. This is climb. And I mentioned climb causes creep, time dependent mechanical deformation of a material. So please read up those things from the textbook. There are many slides which I will not cover here at this point. Now how dislocations are getting generated? They multiply in number. Give me a couple of minutes break. I will be back in 2 minutes. Any questions so far? So a dislocation is moving. Are you there?
Yes, sir.
Yes,
Yes,
sir.
Yes, sir.
A dislocation is moving on a slip plane towards this direction, slip direction. It encounters two fine precipitates, second phase, which inhibits the motion of the dislocation. The particles are strong, dislocations are not able to cut it through. And we are applying shear stress from this end. What will happen is this: dislocation due to the application of shear stress will try to bow, and eventually they will take this shape from here to here and there. If you look at this end, the sign of these two dislocations are opposite due to their nature, planes, their direction, they are present. So these two portions gets joined and this portion gets snapped away. So I create a loop of the dislocation. Now with continuous application of shear stress, this dislocation becomes straight line again, then it starts to form a loop again, just like this, then it will form a loop again, and so on, and eventually it will form. So ultimately what you will have, you will have a dislocation, and there have several loops around it, many loops. So thus from one dislocation, you generated many such dislocation loops. And this mechanism is called Frank-Reed source. Frank-Reed source. So what is the force per unit length acting on this dislocation? This force F. Is tau B. This capital lambda is the energy per unit length of the dislocations, which is GB square by 2. B is the Burgers vector, G is the shear modulus. We are not going for the derivation of this because this will learn next semester. Tau is the shear stress required to bend a dislocation to radius r. This is the radius r. So from there we can come to a relationship. Tau is equal to GB by L. GB by L. Okay. Please switch off the microphone. G is the shear modulus. Small l is the distance of separation between two particles. So some book, they write tau is equal to GB by lambda. Lambda is the, or B is the Burgers vector, lambda is, or less, small l is the distance of separation between two precipitates which is hindering the motion. So how you can increase the strength of the material? If the tau required to bend the dislocation becomes very large, it will be very difficult to bend the dislocation. So plastic deformation will not take place. So the equation is tau is equal to GB by L. L is the distance of separation between two precipitates lying at D and D dash. So if I increase the distance between, decrease severely the distance between D and D dash, L is in the denominator. The ratio becomes very large. So you have to have a very fine precipitates in the matrix. Then and only then you can increase the strength of a material. This is how you strengthen, called precipitation hardening. Towards the end of the semester, the process and the physics will be taught in details. You create fine precipitates. Let me give you a corollary. In your room, you are sitting, you have a broken piece of glass bottle or broken glass, one piece lying on the floor. You know where it is there. If I ask you to quickly go out of your room, can you do so?
No, sir.
Can you? The same glass, please, I break it into 10 different sharpeners, 10 different fragments of glass, and uniformly distribute in your room. Instead of one piece, you have 10 smaller pieces. Can you go out from the room in the same ease, same rate, when there was only one
No,
piece?
sir.
Huh?
No, sir.
No. Now, if I
No.
break the 10 pieces into 100 pieces and scatter around uniformly around your room, what will happen to you? You have tiptoe it to look at it and carefully have to come out from the room if you are with the bare feet, that you should not by mistake step on those broken glass. So similarly, when you form precipitates, make it small. The same volume of precipitate, if they are of very small size, they are uniformly distributed in the matrix, which will result in the distance of separation between them as small as possible, the small L. That becomes small and it is in the denominator. The ratio will be much higher, tau will be much higher, it will be more difficult to deform. So there are materials which are called precipitation hardenable. You increase the strength of that material by forming very fine precipitates uniformly distributed all throughout the matrix. Turbine blade engine, jet engines are made out of nickel-based superalloys. They have a gamma prime precipitate for the same purpose. The aluminium pots and pans you have in your kitchen also has fine precipitate. Next time you board a plane, the body of the plane is an aluminium alloy. It has the same precipitate. When you board the plane, next time look at it very carefully. The plane body. Anybody has ever carefully looked at it? The pieces of aluminium, they are joined together. Are they joined by screws, welding, or something else? Anybody?
So some kind of rivets or something.
Yes. Do you know what is rivet? Any chance?
Yes, sir. They sort of like heat them up and then use like two mushroom-shaped metallic units
Yes.
to squeeze them together.
You have a steel water bucket at home. In Hindi or Bengali, we call balti or balti. Instead of this polymer rubber bucket, water bucket, do you have a steel bucket at home or aluminium bucket? Any chance? You see, the folded metal is joined by riveting. So one metal end and another sheet end overlap. You have a tiny hole through it. You put a pin and both ends, you flatten the pin and join it. It's called riveting. So next time you board a plane, look at it. Its outside bodies are riveted, not welded. Reason? These are heat treated and a very fine precipitates are there. Now if you want to weld it, the temperature is very high. You are melting a portion of it and rejoining it. So this fine precipitates with the heat will become very large in size. So L will be very big. Tau is equal to GB by L. And L is very big means tau is very small, it loses its strength. So never ever heat a precipitation hardened alloy above a threshold temperature. So plain body is never welded, it is always riveted. You see, you want to be an engineer, right? How many of you wanted to be an engineer? I know most of you entered because it is IIT. But how many have joined it because for the love of engineering? Please let me know.
Yes, sir.
You love engineering?
Sir.
Yes, sir.
Or
Yes,
you
sir.
love the IIT system?
No, sir.
You want to be an engineer, when you will return to, no, not return, when you will come to campus, definitely most of you will bring a laptop with you, right?
Yes, sir.
Yes, sir.
Yes, sir.
And you will buy a bicycle on campus to move around.
Yes, sir.
I request you, all of you, to come to your hostel when you will come. Bring a small toolbox, which will have an hammer, few screwdrivers, flatheads, Phillips screwdrivers, wrenches, adjustable one, fixed one, some pliers. Unless you do things with your hand, you'll never ever become an engineer. To be a good engineer, whatever discipline you have chosen to, and in general I'm talking about, you need to know little bit of everything. Little bit of everything. And everything of few things. So to become a good materials engineer, you need to know everything of metallurgy and material science. And little bit of electrical, electronics, computer science, mechanical, chemical, and so on. And this aptitude must be developed. You have to learn how to do things with your own hand. You will never be an engineer if you do things only sitting in the terminal and typing it out on the keyboard. So many of those things I like to discuss and show you that is only possible physically. I pray to God that we will have a chance in future to interact in person and can share my experience with you. And you can share your experience with me so I can learn a lot from you and become a better teacher. Because your feedback, your question is invaluable to me. You may be lot younger than me, not maybe, you are lot younger than me, but my students are my best teachers. Any question? Anybody has any question? You see, if you do not ask question, this side of the land is very lonely. Now I don't see any of your face. I am staring at this computer monitor and microphone on. It is equally difficult as you are staring at your monitor and studying, and I am doing the same thing here. So please ask me some question. Okay, otherwise I will fall asleep.
Okay, sir.
Okay, any question, anybody? If you have an aluminium saucepan at home, look at it. The handle is riveted to that pan. not welded. Check it. So we talked about point defects, we talked about line defects. The third class of defects is the planar defect or surface defect. Twin is one kind of planar defects. When the slip system is very restricted, like HCP material, BCC material, not self-centered cubic, due to the application of shear stresses, the critical resolved shear stress value for all the planes may not be reached. And I talked about unless you reach the critical resolved shear stress value, the deformation, the dislocation will not move. So a portion of the crystal takes a shape which is the mirror image of the undeformed region. We apply a shear stress, the orientation of a part of crystal got changed and it becomes the mirror image of the rest of the crystal. There's an imaginary plane here across which, say, this atom is the mirror image of that atom. This atom is the mirror image of that atom. This atom is the mirror image of this atom, and so on. This one is the mirror image of this one. So this phenomena is called twinning. And this imaginary plane about which we see the mirror symmetry is called a twin plane. Okay. So twin is a, remember, in slip you do not change the crystal structure. Dislocation moves by a integral number of the lattice spacing. In twins, atom movement is such that crystal structure does not get changed, but it is a mirror image of the parent rest of the portion across a twin boundary. And this happens when the slip system is very restricted. Now stacking fault is a defect when the stacking sequence of ABC of FC gets affected. Instead of say ABC, suddenly instead of ABC it becomes AC. So the stacking sequence of FCC or HCP, when there is a defect in it, that is called a stacking fault. It is also a surface defect. So twin is a surface defect, stacking fault is a surface defect. They are associated with an energy that's called twin energy and surface defect energy, surface stacking fault energy. So these are defects in a crystalline solid. They are called surface defects or planar defects, identical defects. So there's another picture of a twin. You can visualize it. This is my twin plane, the blue color one, I'm highlighting it, across which I have twin region with respect to the untwinned region. They are the mirror image of each other. So I want to show you from your detail book. This is a twin did not take place. After twinning took place, the atoms moved. All the atoms moved in the twin region by an amount which is the fraction of his lattice constant. During the movement of dislocations, dislocation moved by a distance one atom spacing in the slip direction. But in the twin, this atom moved by a fraction of an atomic distance here, from here to here, and so on. So in the twin region, every single atom moved by a distance, which is the fraction of a lattice constant. and it took the arrangement in such a way it becomes the mirror image of the rest of the untwinned region across the twin plane. Crystal structure does not get changed in the twin region. Only the orientation of the atoms get changed. Never ever the crystal structure. And every single atom in the twin region moves by a fraction of a distance along a plane towards a direction, particular crystallography direction. And their magnitude of the movement, how much they move, is the function of how far the atoms are lying from the twin plane. So it's just like a military formation in the march past. Everybody is moving by the same distance. So in dislocation, only atomic movement you see in the vicinity of the localized lattice disturbance, that's the dislocation line. But in case of twin, every single atoms in the twin region moves in a particular direction by a fraction of a lattice constant. This magnitude lattice fraction of a lattice constant is also fixed depending upon the position of the atom respect to the twin plane. Imagine billions and billions and billions of atoms in the twin region move by a fraction of an angstrom in the particular crystallography direction instantly. And this is the beauty of the material science or metallurgical engineering. And this is twin. This is the picture. In optical microscopy lab, they will show you. In brass sample, they will show you twins. This entire thing is a grain, inside which these black bands are the twins. This black bands is a twin, and this is exactly what is happening. So every atom in the twin region moves from this position to this position to that position, and so on, by a fraction of a lattice constant.
So what drives them to do so?
When slip system is restricted, you do not reach the critical resolved shear stress value to initiate slip, then twinning takes place. There are two types of twins. One is called mechanical twins. During the application of load it happens, HCP, BCC can show, but face-centered cubic never ever shows a mechanical twin because it has a 12 slip system. If the load is sufficient, at least one of the 12 slip system will be effective and slip will take place. But they show annealing twins. If you subject it to severe mechanical deformation and then heated it at a particular temperature, you create twins in face-centered cubic metals, and they are called annealing twins. You must read up the Dieter's book. Very nicely, all these are explained in Dieter's book. Okay?
Okay, sir.
Any question?
Okay, sir.
Any question? So, couple of points please write down about twins. I'm comparing slip with twins. In slip, the orientation of the crystal. In slip, the orientation of the crystal above and below the slip plane, above and below the slip plane is the same after deformation, is the same after deformation as before, is the same while twinning results, in an orientation difference, across the twin plane, orientation difference across the twin plane. Second point, sleep is usually considered to occur in discrete multiples, of the atomic spacing, comma, while in twinning, the atom movements are much less than an atomic distance. I said fraction of a lattice constant. So what I said so far, I am summarizing it. I repeat the second point. Sleep is usually considered to occur in discrete multiples of the atomic spacing, comma, while in twinning the atom movements are much less than an atomic distance. Number 3 point. Sleep occurs on relatively widely spread planes, comma. But in the twinned region of a crystal, every atomic plane is involved in the deformation. I repeat, sleep occurs on relatively widely spread planes. Remember, pulse stress, that A value. But in the twin region of a crystal, every atomic plane is involved in the deformation. Number 4 point. Twins can form in a time as short as a few microseconds. Twins can form in a time as short as few microseconds. Twins can form in a time as short as few microseconds, comma. While for sleep, there is a delay time. Of several milliseconds. before a slip band is formed. Delay time of several milliseconds before a slip band is formed. Number 5, very important point. Number 5. The lattice strains needed to produce a twin configuration in a crystal are small. The lattice strains needed to produce a twin configuration in a crystal are small, comma. So that the amount of gross deformation that can be produced by twinning, the amount of gross deformation that can be produced by twinning is small. Any question? So twinning is never a major mode of plastic deformation. Slip is. So then what does twin do? You see, if the slip planes are not favorably oriented with respect to the applied load direction, the resolved shear stress on the slip plane in the slip direction does not reach the critical resolved shear stress value. Now twinning takes place. During twinning, the orientation of the plane gets changed. And now those planes which were at an angle with respect to the applied load, which did not result in the critical resolved shear stress value reaching, now their angle is different, and the applied load will create a resolved shear stress component on those planes whose angular relationship got changed. Now they reached a critical resolved shear stress value. So a plane, you applied a load, the resolved shear stress value is not as high as critical resolved shear stress. Dislocation will not move. Now during twinning, orientation changes. So orientation of the slip plane also gets changed. Now if it gets changed in such a way, the resolved shear stress component on it now is equal to or more than the critical resolved shear stress value, the dislocation will start moving. The slip will take place. So twinning results in slips which otherwise was not possible because of the orientation of slip planes for a limited slip system material. Any question?
So can twins be as large as a whole grain?
Please be.
Okay.
I didn't hear you properly.
So can twins be as large as a whole grain?
Larger?
So can they be as large as a whole grain?
Then it will not be a twin anymore because it will be a mirror symmetry with respect to what? Grain boundary is not a plane.
It means two grains placed
So
adjacent
the
to each
grains, they have a misorientation of few degrees. So that's the reason they are called grain, not twin.
other. Okay, sir. Got it.
Okay? That's a good question. Any other question? Is anybody there? Or all are sleeping?
No, sir.
Ask me question, please.
In the fourth point, you said that twins can be formed in a matter of few microseconds. So how do we observe those?
Very
Means
quick, because every atoms are moving. But sleep, you see, dislocation motion is snapping one plane at a time. So it takes longer time, milliseconds. Twins, microsecond.
both are in a fraction of seconds. So do we
That's
continuously
one is
observe them?
micro, one is milli.
Yes, sir. Means how do we observe them? Like do we continuously observe them under
Oh,
scanning
yes,
electron microscope?
experimentally all done. These are all done. I will tell you, means you are in a fantastic branch of engineering. I mentioned that by default you join metallurgy, most of you. But you do not know what a great discipline of science and technology metallurgy is. You can pursue research in any field if you wish. Okay? Anything. I can tell you, other than my research in lithium-ion batteries and sodium-ion batteries, energy materials, nanostructure materials, composite materials. Two are my passions are there. I wanted to be an archaeologist. But being the only child in the family, my parents did not, especially my mother did not want me to become an archaeologist. I wanted to be a geologist. That was my second option. She didn't allow me. She wanted me to be a doctor. After 18 days, I quit and started studying my third choice, that was metallurgy. But I did not give up my passion and hobbies. I still do a lot of archaeometallurgy, did lot of study on those Harappan coppers and others in past. Still from time to time I get samples to analyze. And my passion for geology and also other archaeological stuff. And passion for my geology, I also study meteorites. You know meteorites. They even have publications on meteorites. And that is possible because this metallurgical engineering is basically nothing but physics of materials. So either you want to work in the field of electronic materials, which I did. I was in IIT Madras. My first job in India was IIT Madras. I was there 1 year, 4 months. Then time I had an access to electronic materials lab. I used to work on amorphous silicon, polysilicon, all those electronic materials. So all of you, I can tell you that if any field you want to move or your research interest, that is possible to do it. And people from other fields also join metallurgy. Has anybody got a copy of Kaliti's book? BD Kaliti Extract. The third edition, Indian reprint is there. BD Kaliti passed away in 85, I think. And one of the best textbooks I ever read. But few years back, somebody else became a second author and revised that book. And revision was terrible. So many mistakes. And if I remember correctly, that fellow did his PhD and his undergraduate study was in a completely different field. I want to tell you these things because people from various fields can also come and do material science. And similarly, from material science field, we can also go to different field and do research. So this is a fantastic subject. You see, all the things I'm saying, these are all experimentally verified. This fraction of a second, they move, what is the nanos, whether it is a millisecond or your microsecond. These are all experimentally determined. It's not a hearsay. I will not say anything in this class which is not experimentally verified. If there is any doubt about certain theories of observation, I also mentioned that. Saying that, one day last week I was talking to your class representative. and he expressed the concern that what will happen to internship, right?
Yes, sir.
Are you present in the class? Gauri Vignesh, are you there? Gauri Vignesh? Is he there? You see, he is sleeping. Your CR is sleeping. So he asked me during discussion, what will happen to your internship next year and all those things. I said, don't worry about anything in second year. The third and fourth semester, you learn fundamentals. See, if you do not know ABCD of anything, you cannot write Macbeth. There's the steps. Each step you learn little bit at a time, and then eventually you learn the big things. So third and fourth semester, you learn the fundamentals. Once you have that some fundamental knowledge, you can always apply outside the country and inside the country for summer internship. So those of you who are concerned about that, please don't worry about it. You don't have to do experiments or projects in the lab in the third or fourth semester.
Hello, sir. Still sorry.
Who is there?
Gauri Vignesh, sir. Actually, there was a connection problem. I got disconnected and I joined just now.
I thought it's Friday, you are taking a long nap.
No, sir.
No, that day we talked about, and I wanted to tell your friends not to worry about summer internship and others. The last year, second year students, I wrote recommendation for them for the Canadian fellowship this year. So this will come. Don't worry about those things. Only request of mine, study the fundamentals very, very well. And I'm always there for you. If you have any question, I will be more than happy to explain it 100 times if required. Study hard, understand. I know until JE, you are taught how to write competitive exams. You didn't have the luxury of learning things. The only thing you learned how to crack the test. How much knowledge did you gain? Tell me the fundamentals of physics, chemistry, and math. You are far superior than me in solving problems in physics, chemistry, math. No doubt about it. But do you understand the meaning of those? Every problem you solve, the physics behind that problem? I doubt it. So this is an excellent opportunity for all of you in the IT system to learn. Read as much as you can. You'll never get a chance in your lifetime to learn as much as you can during these 4 or 5 years of UG study. Forget about everything, enjoy your study. And nobody is forcing you to study for cracking the exam or your JE or any entrance now. Just for the gaining knowledge, you read. And read as many books as you can. And this is wonderful discipline of engineering. You see, so many handbooks and books are written by the professional society like American Society for Materials, ASM International. So many handbooks. There is not a single science or engineering discipline professional organization published so many scholastic books. Unbelievable. Any question you guys have for me?
Sir, actually there are many subjects and tests are also there.
Please.
And it is very difficult to understand in online mode. Like we don't have access to all the books and everything. But
look, few books I mentioned, couple of books for $500 approximately, rupees, you can think about procuring it. Tell me, I know I am fully sympathetic to you because it is terrible for me to teach online mode. I am staring at a monitor and I'm seeing the slide which you are seeing it, I can't see your face. It's terrible for me to teach this one. But I have no other option. And I am trying my best to teach you as much as I can to my limited ability. Whatever I learned during those decades, I want to share with you. Whatever knowledge I have, whatever little knowledge I gained, I want to share with you. And you have to learn a lot more than I do. Because every generation learns a lot more, lot better than the previous generations. So there is no other option. Please try to find a way to enjoy this learning process. You see, as much as you are suffering, I am also suffering. That's the reason I always say, any question, please ask me, please ask me. When I'm physically teaching in a classroom, I make eye contact with every single person. And looking at their face, I know that person is thinking about asking a question, but reluctant to ask. So immediately I said, do you have any question? Do you follow this and that? And then that person feels comfortable to ask the question. But here I cannot do that. So whatever we don't have right now, you see, please forget about it. But we have something, no? That is not better than nothing. You look at it, entire life of yours is ahead of you. I have less than 6 years of my job left, then I will retire. Out of which 2 years are gone in the online mode. I'll not get that 2 years back. And I joined IIT Kharagpur because I love teaching. I love my students. I love interacting with my students. And out of this, my entire career, 2 years gone by. I feel terribly bad.
So one more thing, so if it is possible, like some kind of projects or something, if we are introduced to in the online, whatever is possible, if we are introduced to such kind of thing, it will be great.
So, whatever I am teaching, you please give me suggestion and advice. How can I make it better? With the limited resources I have. You see, for you, I have a much better camera. I have much higher resolution, expensive camera we put it. Madam also uses that thing. We also put it last week a new microphone system so the sound quality improves. And one of the friends suggested me that software, but yes, it works little bit with the tab, your iPad, but when it doesn't synchronize with the pen of the iPad, that free software. We tried, but it is not working that well. Few other tablets I was thinking about to try with, then got the feedback is not good. But let me know how can we be more interactive and it will be more fun to learn together.
So you can add some animation or videos like in the slides. So that
video and animation, many of you do not have a good connection. Network issues are there. I tried another course in last semester, it didn't work. You may have a good LAN connection, but many do not. And in my home, the LAN connection is not that great also.
Sir, apart from these slides, can you teach on Blackboard? Or
I
like
have whiteboards, I brought it sitting next to me, we tried, it's not working. The resolution is very poor, you cannot see that.
This mode is okay, sir, like PPT and everything. Actually,
Everything we purchase. I personally purchase and set up a small studio kind of thing at our quarter residence so I can teach better. The big whiteboard with the stand, we tried everything. It's lying just 2 feet from me. Behind my writing desk, I kept it and the stand also there. Then things would have been a lot better, do you know? I got a camera stands, I put a DSLR, other your mirrorless cameras, everything I tried. But you have to remember our bandwidth problem. Even try to create better lighting in the room for live telecasting. And that's the reason, madam,
Sir,
and I teach from home, not from the department, because department cameras and others are not of this quality. What we have set it up at home. The sound is
sir,
better
last
this way,
year,
right? The sound quality.
Yes, sir,
yes,
it's a lot better.
sir, I was saying that last year we had engineering mechanics course where professors used to provide us the recorded lectures, and we had some doubt classes where uh, like student see that recorded videos and they come and ask doubts to the teachers and solve tutorials there.
Actually, in comparison to that, this is more better for all of us, I guess,
Actually, what
because
happens, there is something called NPTEL courses. Those are recorded in a studio atmosphere. Institute had a studio where they record, and you can take nationwide NPTEL courses, get credit. If you pay fees, you can sit for the final exam and you can get a credit on. So those courses, few people did that in NPTEL courses, and they show that. I don't know about drawing things, I cannot comment it. So that is done in the institute studio. Why I did not do NPTEL course is, the reason is this: the slides I show you are copyrighted items from various authors, and I'm allowed as a teacher to use that slide for the classroom setting. That's the reason I request you not to upload these slides on YouTube or any other channel, because then you will be in violation of the copyright. And this is a serious issue, serious matter. Last semester, Government of India, through, I'm forgetting their channels and the DD shows, classrooms, Science something, I'm forgetting their channels, various courses. So the course I teach, and madam, they requested us to go live for all private engineering colleges, state engineering colleges, along with NITs, and if other IITs want, but NITs and these colleges for this Swayam Prabha. But the problem came because we used the copyrighted thing. For every picture I use for this, and whether it is for commercial use or not, I have to take the copyright clearance from the copyright holder for every single one. And this is an Herculean task. Okay. And that's the reason I cannot go to NPTEL, and that's the reason I request you not to share the slides at any other forum or things like that. Then you will be held legally responsible for the violation of the copyright. And nowadays it is pretty bad. But they can go really big time after any person who violates the copyright rule. So I have the last year's video recording. The things I'm teaching, I could have played it and then have question answer session. But I didn't do that because this is the 24th year I'm teaching this course. 24th, and then 1.5 years in IIT Madras, this course, the very first course in the department. Every day I do not write class notes or anything. I read books and teach it. And if you check the last year's recording, you will see every class is different, because you ask different questions, different mode, different settings, and this interaction I truly enjoy. My life would have been real easy if I had showed the last year's recording. I don't have to teach that course, sit there and have question and answer session. But honestly, will you like that? Or this live teaching online mode you prefer?
No, sir, it's better. It's
No,
better.
sir,
Yes,
it's
sir. This is
better.
better. Much better.
Okay. But any suggestion you have which is implementable, I'll definitely do that. Any questions you guys have?
Sir,
Anything?
just a thing out of topic. But sir, in offline campus, how long do we normally have a semester? About 4 months, right? 4 to 4.5 months.
Normally, autumn semester registration starts in the third week of July and class starts third week of July. And then,
And it ends.
and this time of the year you have mid-sem, which is 8 to 9, 10 days long, depending upon holidays and others. Okay. And
Yes,
the
sir.
final exam is towards the end of November.
So we are getting August, September, October. We are getting 4 months. When in offline campus.
Yeah, but that also is defined by the number of holidays, or which days the holidays are. So academic calendar is decided ahead of time.
Yes, no, means I am just including all of those, but for
Approximately,
this year we are getting three months, right?
I don't know.
Because
I have to
we
check.
started we started from I don't know if I am wrong, but from the mid of
August.
August and
Not mid of
will
August,
end.
I think 7th of August, right? Or 10th of August.
Actually,
18th
it
of
was
August.
The
scheduled
15th.
at 7th
I,
August,
I,
but
I started late. The reason was many students did not register, UG students. Many. Many of you did not register. And I cannot tell the name, that will not be appropriate. So if they are not registered, they are starting class and then they miss a week of classes, then what will happen? They fall back. So because of this problem, I had to wait for a week. And thermodynamics class, same thing. Many of you did not register. But in physical classes, even if you did not register, I used to ask them, many a times they didn't show up even. Quite often they showed up. I say, at least sit in the class. And I'll add your name in the attendance book manually.
so sir, I was just asking this because is there any possibility that our next semester, I think so, it would be on online, high chances there.
I
So
have
will
no
it be
idea.
also for 3 months,
I have no
or it can increase?
I cannot,
It
honestly, I do not know the answer of it.
means I am just asking about the duration because a month
I
less
have
in
no idea about
semester
the
is
duration for next semester. Honestly, I don't know. If I come to know, I'll definitely let you know.
okay, sir. Thanks.
I
The
hope by
reason,
now you have realized
yeah,
that I'm pretty upfront and open to all of you.
yes, sir, that's
Whatever
true.
I
That's
know,
true.
I tell you guys, and if some confidential things you ask me, which I'm not supposed to share, I'll openly tell you, sorry, I cannot answer this question. This is confidential. But I will not mince my words. I will not say something in your front and then something else at your back. I'll never ever do that.
No,
So
sir,
if I
that's
come to know, I'll definitely share with you.
So what's your personal opinion? Like, so what's your personal opinion? Lot of personal viewpoint. If you could come when.
Yes, I do not know at this time. Honestly, I do not know.
Oh, okay, sir.
And if I know that, I'll let you know, because I'm still very confused. I have not gone for any meetings in uh, one small conference and maintaining the 10 feet distance and all protocol in Calcutta. I attended in a 5-star hotel. It was a big meeting, and I went there, stayed for 1 hour, gave my lecture, and returned. That was in March when things were much better. After that, I did not attend any physical meeting. And then next week, Tuesday, I have to attend a and I'm still doubtful whether I should go or not. It's a government meeting. And not far away from Kharagpur. It's a 2 hours drive. And if I go, I will have a surgical mask above which N95 mask. So I really do not know. But one thing do you know? one of the most important virtue of a human being is the patience. Please be patient. You will learn this one when you will grow a lot older. So at my age, I really appreciate this fact that have patience. But don't worry, as soon as I get any hints of any development, I shall share with you. But the things which is not under your control, forget about it. Protect yourself, stay healthy, and enjoy study. And enjoy your hobbies too. Life is not only studying, there are a lot more things in life to enjoy. Any question?